Well, hi there. We're about to have a very interesting little look at a fascinating application of compound angle formulae in the area of trigonometry, and it is a cos x plus b sin x. What an alluring title. Well, it certainly is. Compound angle formulae. Okay, Mr. Box. Thank you, Mr. Box. What a topic, eh? Okay, come on, we're going to have a look at this because it is very fascinating. So, we've got to express cos x minus root 3 sin x in the form of r cos of x minus alpha, and hence find the range of the function f of x equals cos x minus root 3 sin x, as well as its maximum and minimum values. Well, now that's only possible without driving your head into a huge conundrum and a big algebraic mess by doing what I'm about to do, guys. Now you just check this out, it's very elegant. So we can say that sin x minus root 3 cos x, cos x minus root 3 sin x equals r cos x minus alpha, right? Now, expanding the right hand side, we do that, which is what you know how to do, isn't it? Cos x cos alpha minus plus sin x sin alpha times r. So now we're going to get the coefficients, the constants, in the front in brackets, okay? And we're going to equate the right hand side to the left hand side. So what can we say? We can say that by equating coefficients, we can say that 1, that's the coefficient of the cos x term, there on the did I do that right? There, that one there, there's a 1 there, okay, and that's equal to this one, okay, that one there. We can also say that this one here, the minus root 3, is equal to the r sin alpha, okay, because we're equating coefficients, they have to be the same. Okay, minus root 3 is equal to r sin alpha. Yes, are you impressed so far? Well, you wait, you ain't seen nothing yet. Therefore, cos of alpha equals 1 over r. I'm just rearranging that equation, and similarly I can say that sine of alpha equals minus root 3 over r. Now, here comes the Wolfie magic triangle. Da-da-da-da. I love this magic triangle. It gets me out of so much trouble. It's just amazing. Now, watch. There's alpha. Hello, Mr. Alpha. Now, let's put your opposite, hypotenuse, and adjacents in according to what's appearing on the left. Okay, so we know that cos of alpha was 1 over r. There they are drawn in. And there, when we know that sine alpha, forget the minus bit for now, but it's the magnitude of it is root 3 over r. Now, I can spot a Pythagoras Theorem happening here, which is going to give us the value of r. And it's very nice. So r squared equals 1 squared plus root 3 all squared, which means that r squared equals 4, and r, being a length, must be just 2. Okay, no negative 2. Right, so now we've got r. So let's replace that that r on the hypotenuse of that triangle with its value, its newly found value, which is 2 for me and you. Now it's even more exciting because we're going to go back to the left-hand side of the screen to over here, and we're going to put 2 there and 2 there, and that will enable us to find alpha. Cos of alpha is a half, yes, and sine of alpha is minus root 3 on 2. Excellent. Now, we're going to use the basic angle, and then we're going to look at the fact that cos alpha is positive and sine alpha is negative to identify which quadrant the equivalent to that basic angle belongs to, and then identify the angle. So the basic angle in quadrant 1, of course, is pi on 3, because sine of pi on 3 is root 3 on 2, and cos of pi on 3 is a half. Yes, but sine alpha is negative, and cos alpha is positive. So come on, which quadrant are we looking at, guys? Yes, of course it is. It's that quadrant, fourth quadrant, okay? So what is our equivalent angle to pi on 3, but which appears in quadrant 4? Well, I think it is 2 pi minus pi on 3, isn't it? Yes, of course it is, which is 5 pi on 3. There you go. So we've identified, we've calculated r, we've calculated alpha, and we've got our new expression for cos of x minus root 3 sine of x, because it is 2 times cos of bracket x minus 5.3, Mr. Box. Thank you, Mr. Box. How marvellous, guys. See, we're just dealing with one trig beastie here, cos, instead of this mishmash over here, which is cos x minus root 3 sin x. It's much more simple to deal with it, because we have to find out the maximum and the minimum of this function and the range. Well, look, cos normally goes from 1 to minus 1, so if it's multiplied by 2, what's it going to go from now to where? From where to where? Yes, I heard you say minus 2 minimum and maximum plus 2, of course, and the range is that thing. That thing there. That's how you write the range. That means from minus 2 to plus 2 inclusive, guys. Now, there's another way we could have expressed that quadrant 4 angle, everybody. If we didn't want to say 5 pi and 3, which after all is a pretty big angle, if you were just keen on an acute angle, you could actually just, instead of identifying this as 5 pi and 3, you could have identified it as minus pi on 3 if you wanted to, by just going in the negative direction. Aha, pretty smart, hey? So therefore, you could say alpha is minus pi on 3, which is a quadrant 4 equivalent angle, and therefore you could have said that f of x equals 2 cos of x minus negative pi on 3, or 2 cos of x plus pi on 3. And Mr. Box, thank you, Mr. Box. Now, how do you like it, guys? It's pretty good. It's pretty elegant. So, yeah, we identified the maximum and the minimum and the range by turning that expression that they gave us into a single trig function equivalent. And I think it's marvellous. So let's go over the page now. Onward, ever onward. Solve the equation. Oh, that's the same expression turned into an equation now. No problem, I know what to do. We're just going to use our newly found equivalent expression for cos of x minus root 3 sin of x. And we know that therefore 2 cos of x minus 5 pi and 3 equals 1, where x goes from 0 to 2 pi inclusive. Now, okay, therefore we're saying that cos of, dividing by 2, cos of x minus 5 pi and 3 equals a half, doesn't it? Now, I know what a basic angle for that is, but I think we're going to work out our working domain first. The working domain, this is how I do things. It's a precise method of capturing my solutions, rather than sort of the scattergun general solution approach to doing it. Now, alright, so what do? Well, stand by, here it comes. If you know that x goes from 0 to 2 pi inclusive, therefore the working domain being what's behind the cos sign, the x minus 5 pi and 3 bit, that means that will go, yeah, you subtract 5 pi and 3 from both the 0 and the 2 pi. See? I've basically said, okay, well therefore x, take away this, must be this take away 5 pi and 3 to this take away pi and 5. What, take away what? 5 pi and 3, which gets us to that and that. Alright? Now, that's what I do. And that'll be the domain within which I work to capture my solutions to this equation. So stand by and you'll see what I do. Okay, but first we're going to find the basic angle. Okay, the basic angle is the angle which has a cos of a half. And you know that's pi on 3, don't you? Of course you do. Now we're going to find the equivalent angles in the quadrants required. We need a cast diagram for that. Here it comes. Now that's the quadrant 1 situation. Okay. So if cos is going to be positive, which quadrants do we want? Well, we do want this one, and we do want that one, don't we? I think so. They're the ones we want. Okay. So now the plot thickens. Capturing the angles within the working domain. Okay, that's why I worked out the working domain in the first place. Now, we've got to go from minus 5 pi on 3 to pi on 3 in the positive direction. Well, we don't necessarily have to go in the positive direction. So we'll just scrub that positive direction bit. We're going to go from minus 5 pi on 3 to pi on 3 using the cast diagram as a guide, okay? So first of all, the negative direction, okay? The negative direction, so just let me make myself happy here by getting rid of that spurious information. Just a minute, stand by, ladies and gentlemen, stand by. don't want you, don't want you. Goodbye. Okay, sorry for the mess. Okay, now that's better. Using the cast diagram as a guide. Now the negative direction, that means we've got to go. The negative direction means that's negative. So what we're going to do is we're going to go from here right around in the negative direction till we get to minus 5 pi on 3, which actually incidentally is there. So on the journey we're going to capture this one, boom, got one, minus 5 pi on 3, keep going, boom, got another one, minus 5 pi on 3. And if we go any further we're out of range, so it looks like we're capturing two solutions in the negative direction. Yes? Good. Now we'll go in the positive direction now. So that means where have we got to go to in the positive direction? Having a look at it, yeah, we've got to go as far as pi on 3 in the positive direction. So let's simulate that. Here's the 0 point. Boom! That's it. Pi on 3. That's as far as you're allowed to go, and we've captured one in that process. So that's the only one. That's pi on 3. Okay. So therefore, x minus 5 pi on 3, our working domain thingy, is going to be pi on 3. So now let's put all the ducks in a row now. Put them in a row and we'll solve for x, okay? And which is what we're supposed to be doing with this whole thing. Okay, now I put them as ducks in a row from the most negative right up to the most positive one. Okay, so I'm saying x minus 5 pi on 3 is. Alright, see them all lined up? That's the most negative one. That's the next one, and that's the positive one, yeah? Now all I've got to do now is I've just got to solve for x by adding 5 pi on 3 to both sides, and I will have my solutions. There they are. There they are. Beautiful, Mr. Box. Thank you, Mr. Box. Now, that's how you do it, guys. That's how I do it anyway, with my working domain technique, okay? Yes, good. Now, onward again. What's this one? I think it's the same as what we've been doing, except we've got some 2x's here. Well, I'm not worried about 2x's. Come on, bring them on. We can do that, can't we? Because we also have a 2x over here. So no need for any panic. Everything's good, guys. So come on, we'll just go through the whole thing again. Now, with this time we have to express it in the form of sine. A little bit different for us, but the same procedure. Okay, so we got root 3 sine 2x minus cos 2x equals r sine 2x plus alpha. Okay, so let's expand out the right-hand side like we're used to doing and collect the constant terms together. Now it's time to equate coefficients, yes? Good. So therefore we're saying by equating coefficients we would say that this root 3 thing there must be the same as this thing, and this minus 1 coefficient of the cos 2x term must be equal to r sine alpha, aren't we? Well, I think we are. So let's do that. That's good, and that's good. That's good. Now, okay, now we're going to solve it for cos alpha and sine alpha. We get that, and we get that, and then we're going to do our magic triangle. Da-da-da-da! And I've put all the relevant sides in to fit with those two equations there, and now we can find r, can't we? Of course, it's 2 again. There we go, beautiful. Now we're going to work out cos alpha and sine alpha without the pronumeral r. There it is. Cos alpha is root 3 on 2. Sine alpha is minus a half. Now, basic angle, cast diagram, equivalent angle, done deal, guys. Yeah, there it is. There's your cast diagram. Basic angle is going to be pi on 6 this time. Pi on 6 now for something completely different. Pi on 6. Now, which quadrant? Now, that's the question I want you to address. Okay, now sine is negative, cos is positive. Which quadrant? Yes, that's the one, quadrant 4. It is, isn't it? Okay, so therefore, quadrant 4 is needed, and we know that I'm going to call it minus pi on 6 now for something completely different. You could call it 11 pi on 6, but I can't be bothered calling it 11 pi on 6. Let's call it an acute angle and call it minus pi on 6, yes? Therefore, we're saying that root 3 sine 2x minus cos 2x is equal to 2 sine 2x now plus alpha is minus pi on 6. Don't get that messed up. And Mr. Box, thank you, Mr. Box, How did you like that? It's good, isn't it? It's really terrific. Now, we're going to sketch a graph. Oh, I hate sketching graphs. Yuck. Oh, well, don't worry about it. Come on, we're going to sketch the graph. Oh, what happened there? Just excuse me a minute while I get my act together. We're going to sketch the graph of that thing. Now, therefore, we can say that sine x plus root 3 cos x is equal to r sine x plus alpha, can't we? I think we can. And we're going to find out what r is and what alpha is, and that's going to enable us to know what we're dealing with here, a single trig function which we can graph. Okay, I don't know how to graph sine x plus root 3 cos x except with addition of ordinates, which is a big mess. Okay, we don't want to do that. Now, so there it comes. I've expanded out the right hand side, collecting the constants like I've been doing for the previous two examples, and equating the coefficients we get. Here we come. We can say that. Now what can we say? We can say that this coefficient here, the 1 here, equals that, and we can say that the root 3 here equals that beast, can't we? Yes, come on, let's go. So therefore r cos alpha equals 1, yes, and we can say that r sin alpha equals root 3. Same deal, same deal. Therefore cos alpha is 1 over r, sin alpha equals root 3 over r, magic triangle. And there it is, and r is 2 again. Heavens, we're getting a lot of 2's going on around here. For yes, that's right, r is 2. Now, we can now solve for the actual value of cos alpha sin alpha. Yes, 1 over 2, root 3 over 2, my goodness. And these are both positive ones, guys. This is a quadrant 1 angle, isn't it? Because they're both positive. And the angle that has a cos of a half is pi on 3. You knew that, didn't you? Yes. There you go. Good. So we've got it, haven't we? We've got it. So therefore f of x is 2 times sine of x plus pi on 3, where x is going to go from 0 to 2 pi. But I'm sorry to tell you, I'm so desperately sorry to tell you, now we've got to fiddle with all this absolute tedium to get the graph sorted out. Now, you're not used to doing trigonometric graphs yet, but I'll give you a little bit of practice here. Okay, this is the patented Wolfman technique for doing trig graphs, but it doesn't make it any less tedious. It is tedious, the most tedious part of the entire methods course. Yes, because you do it in methods. The amplitude is the distance that the thing oscillates either side of the central axis, which in this case is 2. Okay, so this one's going to go from -2 to +2. Okay, that's what it's going to do instead of -1 to +1, because it's multiplied by 2. Now this little thing over here tells you that it's translated pi on 3 units to the left compared to the normal sine x function. Okay. Alright, sketching the graph, here we go. We've got all this stuff to work out. The working domain, first of all, okay, same procedure as before. If x goes from 0 to 2 pi, therefore x plus pi on 3 is going to go from pi on 3 to 7 pi on 3, just adding pi on 3 to the 0 and to the 2 pi, respectively, to get pi on 3 and 7 pi on 3. Okay, now, alright, that's the first bit. Now the y-intercept, that's an easy bit. We just make x equal to 0. When x is 0, okay, we're going to say, therefore, f of 0 will be 2 sine of 0 plus pi on 3. Sine of pi on 3 happens to be root 3 on 2. So therefore, 2 times that will get us root 3. So that's telling us that our y-intercept is 0 and root 3. Now we've got to do some more of this nauseating tedium. Oh dear. Never mind. We'll make it fun. X-intercepts now. Now this is where our working domain kicks in. The x-intercepts, that means that the working domain was that. Yes, we calculated it just over the page. Now, y's got to be 0 for the x-intercepts. Now, normally, sine x equals 0 at 0, and then repeat, then every pi from there on. Okay, so what we're saying is within our working domain, the thing behind the sine, which is x plus pi on 3, must equal that in this instance. Yes, because it's sine of, you can call the x plus pi on 3 like blob. So sine of blob equals 0 pi 2 pi 3 pi da 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 da. Therefore, okay, blob must equal 0 pi 2 pi 3 pi. Therefore, you can then solve it for x. Okay, because blob is x plus pi on 3. You know what I'm saying? I hope you do. And the naught is actually out of range because remember, our working domain is from here to here, and we're talking about this beast, okay? When this beast is naught, okay? Okay, so this beast is naught when you're going from here to here, okay? That's what I'm saying. Now, okay, that one's out of range as well. So it looks like we've just got, now just check, 3, what did I say, 3 pi. Well, that's 9 pi over 3, and you're only allowed to go to 7 pi on 3, see? This one, pi is more than pi on 3, so that's alright. 2 pi is more than pi on 3, but it's only 6 pi on 3, which is still less than 7 pi on 3, so it's okay. Do you get it? So I've got all my solutions now. I've got them organised, guys. Now I'm going to solve it for x. Therefore, x will be subtracting pi on 3 from every term. You get that. Okay, so they look like my x-intercepts. Okay, they are. That implies we've got 2 pi on 3 and 0, and 5 pi on 3 and 0 as my x-intercept coordinates. Okay, so we've done that now. Endpoints. Yes, there's more. Endpoints. Now you've got to put endpoints in when you're sketching a graph with a trig graph with a certain restricted domain. Yes, you do. So when x is 0 and when x is 2 pi, we need the actual value of y. So when x is 0, we already did that because that was our y-intercept from earlier. So that was root 3. So that means that's our one endpoint. When the other one is when x is 2 pi, you get f of 2 pi is 2 sine of 2 pi plus pi on 3, which is just the same as 2 sine of pi on 3. And you get root 3 for that. Bang, root 3. So that means we've got 2 pi root 3 is the coordinate of the right-hand endpoint. Yes! Now, are we finished yet? Oh no, the quarter cycle step. Yeah, this is a very important part of this, of me drawing sine and coses. The period of this beast is 2 pi, alright? Therefore, a quarter of a period, which is what I call the quarter cycle step, which you'll notice why in a minute, is a quarter of 2 pi or pi on 2, okay? Now, the starting point, the last thing I need, the normal natural starting point of the sine graph when x is 0 is x is 0, y is 0. Yeah? That's what I'm saying. Now, this one is translated, isn't it? Yeah, so we're saying x plus pi on 3 is the thing behind the sine, S-I-N, sine. Yeah, if that equals 0, then what is x? X will be minus pi on 3. So that is the natural starting point of this trig graph because it's been translated over to the left by pi on 3. So it'd be minus pi on 3 and 0, but actually that is going to be just as a guide for us because, do you know why? Because that'll actually be out of range because x is only allowed to go from 0 to 2 pi. See? But it still helps to work it out, guys. It gets you the proportion and the perspective of what is going on with this thing because they're beastly to work out, you know? So, and we're ready to graph. Yes, let's go over the screen and do it. Excitement plus. Now, here we go. Put all your axes in. Work out what your x scale's got to be. I'm going to do it in twelfths because we're talking about a pi on 3 translation, which is 4 pi on 12, isn't it? That just helps me to think better. So I've drawn that in. I've showed that in there for you. There's one little notch along the left-hand side is pi on 12. I actually draw these lines, the extremities of the y in here, not as asymptotes, just as guides to help me sketch the thing, okay? Right? That's why I do that. Now, let's just put our starting point in, but it's not going to be within our actual required domain, but I'm going to put it in anyway because it helps me figure out where to start the graph, yeah? So I've put it in as a kind of a minus pi on 3 or minus 4 pi on 12 and the y value 0. And then I'm going now. My quarter cycle step is a pi on 2 or 6 pi on 12 or 6 of those little horizontal graduations for the graph squares for the x. Okay? Now, see what I'm doing, guys, is I'm going from the starting point. I'm going over to the right by pi on 2 or 6 little squares, and I'm going in the process from the central axis up to the extreme, y value in the positive. Now I'm going to count 6 more squares to the right, and I'm going to get back to the central axis, which is there. Now I'm going to count 6 more squares, and I'm going to get down to the lower extremity, which is there. Then I'm going to count 6 more squares, and I'm going to go to the central axis again, which is there. See how I do it? And then I'm going to finish the beastly thing off by the end point, which is there, which is root 3 at 2 pi, alright? Now, okay, right, you ready? Here we go, we're going to sketch the thing now. Okay, now I do it in quarter cycle steps. That's why I call them quarter cycle steps. So I'm going to go from the starting point as a dotted line till I hit the y-axis, which I'm going to rub out afterwards. Then I'm going to go to the first quarter cycle. Oh, sorry, that's the end point. Yeah, I put the 2 end points in, I forgot that. Yeah, they're the 2 end points. That's the left-hand end point, okay, which is also the y-intercept, okay? Now I'm going to sketch it. There it goes. There's the first quarter cycle with the... I'm only dotting the first bit till you get to the y-axis, because that's not supposed to be in it anyway, and I'm going to rub it out in a minute. Okay, so there's my first quarter cycle, which is only a little bit of a quarter cycle. Now here comes my second one. Kaboom, okay? And here's my third one, kaboom. And there's my next one, kaboom. And there's the next one, there's the final one. That's it. Now, okay? Now you've got to put in all your intercepts, endpoints, and as coordinate points, and then I think Bob's your uncle. There's those endpoints, and here comes the x-intercepts. There they are. There they are. Now I think that's just about... Oh, you know, I've rubbed out that bit, that construction bit on the left-hand side, and I think that's it. I think that's it. Yes, it's a lot of trouble. Yes, it's tedious. Yes, I don't like doing it. But yes, it's on the course. There you are. And here's the calculator version of it, okay? And it's a lot easier to do it on the calculator, let me tell you. But it is the same shape, okay? It is the same shape, a bit more squashed looking in the x direction, but there it is. There's all the points. I've drawn them in for you, okay? So, and I think you're a star. Yes, you are. You're a star and you'll go far. So that's it, guys. That is a cos x plus b sin x. And it's all about simplifying a function which has something cos plus something sine, where the somethings are numbers, and reducing that to a single trig function so you can actually work with it much more easily and predict what it's going to do. Okay, thank you for listening to me with this little presentation. I hope you get something out of it, and I hope you enjoy using it, okay? Alright, we'll see you next time. Bye for now.